Hello, my name is Alamutad Dasa from Addis Ababa University School of Pharmacy from Medicinal Chemistry stream. Today we will see the structure-activity relationship of different compounds, different antibacterial drugs, including cephalosporins, aminoglycosides, tetracyclines, and the quinolines. Please don't forget to subscribe, share, and like my video. Let's see the structure-activity relationship of cephalosporins. This is the structure of cephalosporin. This is the general structure of cephalosporin. Unlike that of penicillin, cephalosporins, they have a 6-membered dihydrothioazine ring. This is dihydrothioazine ring. This is the dihydrothioazine ring, that is 6-membered dihydrothioazine ring. In the case of penicillin, it is thiazolidine ring. The beta-lactam ring is fused with thiazolidine ring in the case of penicillin, but in the case of cephalosporin, the beta-lactam ring is fused or connected with 6-membered dihydrothioazine ring. That is the difference. Generally, penicillins, they are more reactive than cephalosporin because of the ring strain, but cephalosporin, they are less reactive in comparison with penicillin. Here in the nomenclature of the cephalosporin, number 1 is sulfur. This is number 1. Sulfur is number 1. This is 2 position. This is 3 position. This is 4 position. Nitrogen is 5. This is 6 position. The acyl amino side chain or RS3 position is 7 position in the nomenclature. Sulfur is not essential for activity. At 1 position there is a sulfur. That sulfur is not important for activity. Sulfur can be substituted with other elements like oxygen, carbon. The activity is retained constant, similar. And this cephalosporins, they have substitution at 3 position here. This is called 3 position. We have R2 substitution at 3. That R2 position is very important for chemical and the metabolic stability of these compounds. Also determines the acid stability. Here, this is also important for new generation of cephalosporins. Many generations, they differ from each other by this substitution or acyl substitution. For example, here in the case of some derivatives, the presence of the halogen atom or alkyl substitution or alkoxy substitution at R2 increases stability, acid stability, chemical stability. Also, they have greater effect on antibacterial potency. This R2 substitution or 3 substitution. 3 substitution is very important. In fact, the other substitution like acyl esters or heterocycle, they are possible. They are possible, but they are not orally active. They are not acid stable. Only those that contain chlorine or other halogens or alkoxides or alkyls at this position, they are orally active and they are acid stable. Therefore, many of the cephalosporin generations, we have first generation, second, third, fourth, and the 5th generation cephalosporin. Therefore, one of the sites where cephalosporin they may differ from each other is this 3 position. 3 position. That 3 position is essential. The 3 position halogens, alkoxides, alkyls, they are important for acid stability, oral activity, but we have also other groups like ester, acyls, heterocycles. They are also good living groups for activities. At 4 position, we have free carboxylic acid here. That free carboxylic acid is important for duration or product formation. It's very important for drug formation, for product formation, for absorption, for salt formation. That is essential. The beta-lactam ring is very important. The bicyclic system is very important. The 2 cycle like that of penicillin, they are very important. The carbonyl group is very important. And at the 7th position, we have the R group. R3 group here. Here we have R3 group, and we have at 6th position, we have hydrogen. That stereochemistry is very important. The CC stereochemistry is very important. At 7th position, the presence of R is essential. It will determine the beta-lactamase stability. It's very important for beta-lactamase activity. The 7th position or R3 position. In my case, it is R3. Therefore, compounds that contain halogen, compounds that contain alkoxy group at R3 position, they are beta-lactamase stable. Also, cephalosporins, they have acyl side chain or acyl amino side chain, the green one. That is also very important. It's important for semi-synthetic incorporation. Newer cephalosporins, they may differ from each other by this group, in addition to the 3 position. 3 position is important also for newer classes, newer derivatives, newer semi-synthetic forms. Also, the R1 position, the acyl side position, is important for newer analogs, newer generations of cephalosporins. Also, it determines beta-lactamase activity. The beta-lactamase stability of some cephalosporins also depends upon this acyl side chain, R1 substitution. Also, additionally to beta-lactamase stability, spectrum also depends upon this substitution, acyl amino side chain. Very important for antibacterial activity. It affects the binding of beta-lactamase enzyme. It will shield the beta-lactamase enzyme or the beta-lactam ring from the enzyme called beta-lactamase enzyme. Very important site for activity. Then another compounds that are essential for treatment of bacteria. At the beginning, we start the classification of antibacterial agents by their mechanism of action. The third classification is in those compounds that will interact with the plasma membrane, like bastracin, neomycin, polypeptides. They are also essential compounds. The fourth one, antibiotics that can inhibit, interrupt the protein synthesis, like chloramphenicol, gentamicin, aminoglycosides, tetracycline. They are also important compounds that are used as potent antibacterials. Let's see the structure-activity relationship of tetracycline. Tetracycline is a broad-spectrum bacteriostatic compound, very important compound for treatment of large number of bacterial diseases. When you see the structure of tetracycline, this is the general structure of tetracycline. This is the general structure of tetracycline. There are 4 rings. By the way, the 4 rings, they are essential for activity. All derivatives containing fewer than the 4 rings, they are inactive. Therefore, for antibacterial activity, there must be 4 rings. This is how to nomenclate tetracyclines. This is the first ring, the second ring, the third ring, and the 4th ring. A, B, C, D rings. Numbering will start from the A ring. That is number 1. Very essential for activity. The simplest tetracycline derivatives that retain the characteristic broad spectra, beta activity, they are 6-demethylated and 6-deoxytetracyclines. What does it mean? The compounds tetracycline derivatives that contain no alkoxy, no OH group, no alkyl group at 6th position. They are potent compounds. This is the 6th position. This is the 6th position. Tetracyclines that contain no hydroxy group. Here, no hydroxy, no alkyl group. They are potent. They are broad tetracycline derivatives. Also, tetracycline that contain enols. Here at 1, 2, 3, mainly at 2, 3 position, there is enolic group. This is enolic group. This enolic group is essential for activity. Very important for activity. Essential. Also, at 2 position, here we have amide group. Here we have amide group at 2 position. This amide is essential. Conversion of this amide into aldehyde or nitride will abolish activity. Also, monoalkylation of the amide nitrogen reduces activity. What does it mean? There is an amide group here. Mono, that means making that nitrogen into secondary group will decrease activity. Therefore, amide group must be retained as unsubstituted for better activity. The dimethyl amino group at 4 position must be alpha orientation. The dimethyl amino group at the 4 position must be the alpha orientation. Removal of that 4 dimethyl amino group reduces activity. You can see here, this is the 4 position. There are amino alkyl group at 4 position. Epimerization also affects the activity. Also loses, mainly the removal can lead to loss of activity. The dimethyl groups, they are very important at alpha orientation for activity. They are important for activity. Also, another very important, the A ring and the B ring, if they are cis-fused with 12A substitution, at the 12A position we have OH group. This OH is 12OH, 12AOH. This group, this 12AOH. The AB ring, it must be cis with this group for better activity. Esters here, they may produce inactive compounds at 12A. Therefore, they can be readily hydrolyzed in aqueous media. That's why they are inactive compounds. Alkylation at C11 position. Here we have C11 position. This is C11 position. Here we have C11 position. Therefore, alkylation at C11 position also leads to inactive compounds. Here we have C11 position. Sorry, this is C11. This is C11 position. This is C11 position. Therefore, conversion of that double bond oxygen into alkyl leads to inactive compounds. Also, dehydrogenation, removal of hydrogen to form a double bond between C5A and C11. This also decreases activity, meaning that at 11 position, conversion of that group, we have double bond here, we have double bond here. Therefore, losing this double bond and making a double bond, a new double bond here, C5 and C11 position will lead to loss of activity. Essential. Therefore, when we see the structure activity relationship of tetracycline, substitution, mainly substitution at 5 position, this position, 5A, this position, 6 group, 6 position here, 7, 8, 9, this may produce compounds that are hydrophobic. Other substitutions, not OH group at 6 position and not methyl group at 6 position. Other groups, they may increase hydrophobicity, lipophilicity of these compounds. Many of these tetracycline derivatives, they vary from each other by having these substitutions. They are important antibiotic compounds. Also, antibiotic activity was improved by varying substitutions in these places. That is essential A 5-hydroxy group in the case of oxytetracycline and doxycycline also may affect the pharmacokinetics and water solubility, and they are orally active, acid stable. 5-hydroxy groups, they are essential. That can increase oral activity, that can increase water solubility. Also, they have effect on pharmacokinetic profile of that compound. As I said at the beginning, removal of the 6 hydroxy group, removal of alkyl group, which is found at the 6th position, this will increase lipid solubility also. Also increases stability, oral activity will increase. If there is no hydroxy group, no methyl group at 6th position, it will increase oral activity, it will increase stability, lipid solubility also will increase. Also, the more useful results have been achieved with introduction of substance at C7 position. C7 position is important. Therefore, different substitution at C7 is important, mainly second tertiary amine groups that will increase antibacterial activities. Alkyl amino groups, they are very important. Also, the most fruitful site for CME synthetic derivatization of tetracycline is modification at 6 and 5, 7 position. These are very important structure activity relationship of tetracyclines. Let's see the structure activity relationship of aminoglycosides. These are compounds that contain sugar with amino substitution. They are also important compounds. Unlike that of other antibacterials, these are known with bacterial resistant development. Most of the drugs, they were resisted by bacteria. Most of the time, they are also given in combination. Let's see the general structure of these aminoglycosides. Aminoglycosides, they may contain 3 or more than 3 cyclic groups. Most of them, they have 3 sugars, 6-membered sugars. These 6-membered sugars, they were classified into 3 main classes: ring 1, ring 2, ring 3. Or you can say ring A, ring B, and ring C. Therefore, in my case, this is ring 1. This is ring 1. This is ring 2. This is ring 3. Therefore, all of them, they are important for activity. Mainly, ring 1 is very crucial for antibiotic activity. Also, the spectrum of many of the aminoglycosides will depend upon the ring 1. Also, the bacterial inactivating enzyme binding ability also depends upon this ring 1 structural modification. Therefore, this is also the primary target for inactivation by bacteria. Therefore, this ring is very important. Amino substitution here at C2 and C6 is very important, both substitution. Here, this is a general structure of aminoglycosides. Let's start from the ring 1. This is ring 1. Substitution here at 2 position and the 6 position is very important, mainly amino group that will increase potency for many of the aminoglycosides. But amine groups, they may be the site for inactivation here. Therefore, if the methyl groups, they are substituted here, they inhibit the inactivation. Amino function, they are important at both position, 2 and 6 position. Therefore, addition of alkyl group will decrease the inactivation. Methylation of either of the 6' carbon or the 6 amino position confers resistance to enzymatic acetylation of the 6 amino group. Therefore, the amino group is at 2 position and 6 position, they are essential. 2' and 6', they are important, but they can undergo enzymatic inactivation. Therefore, to inhibit enzymatic inactivation, it is important to introduce methyl or alkyl groups here. Very important. The 6-amino group is a target for inactivation by aminoglycoside acetyl transferase enzyme. Therefore, substitution with alkyl or alkyl amino decreases inactivation in this place. Therefore, amino group substitution at C2 position is important for activity, antibacterial activity. Hydroxy group at C3 and C4 position is not important. At C3 and C4 position. Hydroxy group here. At C3 and C4 position. It is not important because the removal of the OH group decrease in activation. If there is OH group here, it can undergo inactivation. Therefore, the OH group is at C3 and C4 position, they are not important. If there is OH group, it must be protected. Otherwise, it can undergo inactivation by the enzyme. And the second one is ring 2. This is ring 2. This is ring 2. On ring 2, few modification is also possible. Functional groups are possible without appreciable loss of activity in most of the aminoglycosides. The one amino group is essential for activity. At one position there is amino group. That amino group is essential for activity. Also, it must be protected to inhibit inactivation by the enzyme. Introduction of OH group at C2 position also important for resistance. These compounds, they have or may have OH group at C2 position. This will increase resistance. 2 position means this position. Amino group at C3 position is target for acylation. Here you have amino group at C position. Therefore, it is susceptible for enzymatic inactivation. Therefore, removal of that amino group is important. Also, it increases resistance for such type of compounds. The third one is ring 3. Ring 3. This is ring 3. This is also important for activity. Mainly, it is less sensitive to structural changes, like that of ring 1 and the ring 2. The 3' amino group is very important. Introduction of amino group here is essential for activity of these compounds. Therefore, this is a structure-activity relationship of aminoglycosides. Let's go. The structure-activity relationship of macrolide antibiotic compounds. Macrolides, they are compounds that contain macrocyclic core like erythromycin, roxithromycin, azithromycin, clarithromycin. They are common type of compounds. Let's see the structure of erythromycin. This is the structure of erythromycin, one of the most popular type of compound. It is also the first compound among the macrocyclic macrolide antibiotics. Here, in the case of erythromycin, here we have it is macrocyclic compound. The modification here, this is 9 position. The removal of the 9 keto group coupled with incorporation of a weakly basic tertiary amine into the macrolide ring decreases lipid solubility. Macrolide ring increases the lipid solubility and stability for acid degradation. Therefore, conversion of this this ketone functional group or 9 carbonyl group into nitro group, like this tertiary nitro group, this will increase acid stability. This will increase lipid solubility. Therefore, the introduction of basic amino group will increase activity. Also, in the case of clarithromycin, in the case of erythromycin, here we have at this sixth position here, this compound, it has a hydroxy group here. This is a hydroxy group at the sixth position. This hydroxy group can undergo easily hydrolysis or inactivation. Therefore, if this hydroxy group is protected in the form of ether or alkoxide, the stability will increase, oral activity will increase, bioavailability will increase. This also reduces the effect on the GI. Unlike that of erythromycin, clarithromycin has, here look the structure of clarithromycin. Here in the case of erythromycin, here we have at sixth position, here we have methyl group and hydroxy group. In the case of clarithromycin, the hydroxy group is protected in the form of alkoxide or ether. This will increase stability. This will increase bioavailability. This will increase also solubility, lipid solubility. Very important. That is the structure activity relationship. Among this one, azithromycin, it has 15 atoms in a ring, but the others, they have 14 atoms in a ring. This is number 1 in the nomenclature of these compounds. This is number 1. This carbonyl carbon, lactone carbon, carbonyl carbon is number 1. This is number 1. This is the structure activity relationship of these compounds. Thank you so much. Don't forget to subscribe, like, and share.